All right, welcome, and yeah, stoked to be here to talk to you today about the hidden treasures of crash reports. So my name is Patrick Wardle. I am the CEO and co-founder of W, and also the founder of the Objective-C Foundation. And yes, I am the one up here on the stage today, but this talk is really about you all, because today I'm going to be playing Matchmaker with the goal of making you fall in love with crash reports. So before we begin, I need a hand raise of everyone who already has a deep sense of appreciation or love of crash reports. Anybody? Okay, awesome. The rest of you, we'll see if we can change that by the end of the talk. All right, so before we begin, let's just, deep breath in, deep breath out, open our minds, but also our hearts, because we're going to try to fall in love. All right, so I like to start my talks with a little description about what I hope to teach you all today. So in a nutshell, this will be understanding crash reports, largely on macOS. And we'll see that from these crash reports, we can extract a myriad of information that will allow us to uncover malware, bugs, and much, much more. Now, you might be wondering, okay, well, who cares about crash reports? Answer, everybody. But this includes, and we'll look at these a little closer, users, developers, security teams, and even hackers. So now, when you think about crash reports, you're probably thinking about how they are useful to developers, because as we will see, crash reports hold information that allow us to, as developers, fix our software. But if you think of the average users, crash reports should be important as well. So imagine user is using their favorite application. It unfortunately crashes for the user. That's annoying and frustrating. What's the goal for the user here? To probably get this application or piece of software fixed. And the best way to do that is at least to grab the crash report and provide that to the developer. Here's an example. I am a fan of Hopper. It's a disassembler. Fortunately, like most software, it has some small bugs. And so when it crashes, what I do is I grab the crash report and send an email to the developer explaining what went wrong, how to reproduce it, and then armed with the crash report, he is able to often very quickly fix the software and push out a new version. So he's stoked because his software is less buggy, and I'm stoked because, well, it's also less buggy. So win-win. Now, that's a very common case, but I also want to talk about other cases where crash reports are very valuable. And one of those are to security teams. And the idea is that oftentimes exploits are not 100% reliable. That is especially true today, where a lot of operating systems now have anti-exploitation mechanisms, which make especially memory corruption vulnerabilities not 100% reliable. And if an exploit crashes, this is going to generate a crash report. So if security teams or operating system vendors are ingesting those crash reports, they have the potential to uncover failed exploitation attempts, which in some cases might be previously unknown or zero-day vulnerabilities. I love this great case study from Microsoft, which illustrated out of the millions of crash reports that they ingest, they found two that when they analyzed them, realized that the reason the crash reports had been generated is that adversaries were using what was at the time a zero-day vulnerability that impacted every version of Windows, giving the adversaries, the attackers, the ability to remotely infect any Windows system. Insane. But via the crash report, Microsoft was able to find the underlying flaw and patch that. Super powerful stuff. Security startups, especially on macOS, are also very interested in crash reports, as they should be, because on iOS, we really can't do that much in terms of on-device security tools. But by analyzing crash reports, again, we can find perhaps failed exploitation attempts or even malware that has surreptitiously infected the device. Some examples, ZecOps was acquired for a decent amount of money by Jamf, thus really indicating, I think, the value of crash reports. And iVerify is another company doing some really neat analysis on crash reports. Again, though, predominantly focused on iOS. Now, if you're creating malware detection products, you should also be very interested in crash reports for the simple reason that malware is somewhat buggy and actually often crashes a lot for two reasons. First, malware authors are generally not as, let's say, competent as maybe operating system vendor engineers, so malware is often not as tested as well or written as well, which means it crashes. Also, malware is often pushing the envelope, perhaps using private APIs, doing kind of things that are a little strange, which often means, sure, if the operating system perhaps is updated, that may result in the malware crashing. So the idea is if these tools can ingest crash reports, they can perhaps detect that something has crashed and then analyze what has crashed and see maybe, hey, this was an unauthorized piece of software that perhaps is malware. Some great examples are Stuxnet, the greatest piece of malware ever written. It was, unfortunately, detected originally via crash reports. More recently and more relevantly, at least in the context of macOS, is a malware sample known as Zuru, initially undetected but had some bugs, meaning that on certain macOS systems it would crash. Again, if tools were ingesting that crash reports, they could have detected this malware where traditional signatures had otherwise failed. Malware analysts, in my opinion, should also be interested in crash reports. Here's an example why. So when I'm analyzing a piece of malware, a lot of times I need it to run to completion, both so I can dynamically analyze it to figure out what it does, but also so I can test my detection capabilities against it. So the Lockbit ransomware gang recently had a new macOS variant, ransomware targeting macOS. Unfortunately, it had a bug, which means when it ran, it would crash pretty early on before it actually had caused any damage. I mean, this is good for Mac users. The impact of this was really not that significant. But for malware analysts, this was problematic. So what I had to do was analyze the crash report, figure out where the bug was in the malware, patch it at the binary level for testing purposes only, and then I could run the malware, which now no longer crashed, and confirm that my detection capabilities could generically thwart the ransomware. Again, this was all possible because of the crash report. Next, we have hackers and intelligence agencies. This, to me, is super interesting. So according to the press, the NSA previously was collecting Windows error reports. And this is because, well, two reasons. These reports had a lot of very specific information about the systems that had crashed. For example, the operating system version, the language settings, et cetera, et cetera. These are all very important and information you need when remotely infecting a system. So if you can get this fingerprinting information from a crash report, that's super beneficial. And then also, this could potentially reveal exploitable security vulnerabilities on a remote system. So I love this image. It's a little hard to read, but it's a leaked image from what is supposedly an internal NSA slide presentation, and they photoshopped the Windows error dialog and basically changed the text. Instead of saying, hey, this is going to Microsoft, it's like, no, it's actually going to the NSA so that they can hack more systems. So very creative, and again, showing that crash reports are also very interesting and very valuable even to intelligence agencies. And then finally, in my opinion, crash reports are super important because in some senses they are an absolute truth. And let's look at a very recent example involving CrowdStrike. CrowdStrike, obviously, caused a problem for many systems around the world. But originally, when Windows systems started crashing, who did everyone blame? Microsoft, which was totally understandable. The average user sees a blue screen. They're not going to be like, that's CrowdStrike's driver. But once we got a crash report, we could very quickly see that this was not a Microsoft bug at all, but rather CrowdStrike's kernel driver crashing. And just because you have a crash report, though, doesn't mean you're going to understand exactly what's going on, right? You still have to have some knowledge, which I'm going to talk about next, in how to read it. So this was also problematic because we had people taking screenshots of crash reports, drawing squiggly red lines, and then making wild claims about the underlying cause, which were completely wrong, but were getting retweeted by everyone. The reality is, if you really looked at the crash report and understood it, you could figure out exactly who was at fault and why, which I think is also very, very important. All right, so hopefully I've shown you that crash reports are useful not just to users and developers, but to security teams, malware detection products, hackers, intelligence agencies, and others. I now want to spend some time talking about crash report basics. So, well, what is a crash report? I've mentioned this many times already, or at least mentioned the term, but haven't really defined it. In a nutshell, it is a file generated by the operating system when an application crashes. There's an article by MacPaw that gives a good introduction, and basically they explain that it's kind of difficult for the average user to read because this crash report, yes, it has a lot of very interesting information, but it's pretty low level. So you've got to have like some understanding of it, which is what we're going to learn today. You might be wondering where crash reports are stored. On macOS, if you open the console application and click on crash reports, you get a nice list. Or you can go to either of the two diagnostic reports directory and look for crash reports. They're going to end in the .ips file extension. So what I want to now do is go through a demo. We're going to start with some buggy code and then show you how, in the crash report, we could work back to understanding exactly what went wrong. We're kind of cheating here because we have source code, so I'm going to point out the bug already. But it will show exactly how we could do that. And then the rest of the cases, we will work backwards from the crash report to see what the underlying flaw was. So top left, we have some buggy code. Basically, what we're doing is we are declaring a pointer, and we're setting its value to null or 0. I'm sure many of you already know this, but if you dereference a pointer that points to 0, that is going to cause a crash. That is known as a null pointer dereference. So if we compile and run this, no surprises here, it crashes. Behind the scenes, macOS creates a crash report for us that then we can go analyze. If we open it, we can see it contains some basic information, for example, the path and name of the process that crashed. Also the version. This is important. Imagine you have multiple versions of your software deployed. Well, you need to know which version crashed. There's also information about the operating system. This is valid as well. This is one of the things that, hypothetically speaking, the NSA was interested in reading crash reports, fingerprinting versions of the systems that were crashing. But for example, for a developer, maybe it turns out it's actually a bug in the operating system and not in their code. The next thing that's really important that we can pull out of the crash report is the crashed thread and exception information. So most processes are multi-threaded, so we need to know what thread crashed. That will be told to you in the crash report. Then there's some also what I refer to as basic exception information. Here we can see that the operating system has identified that the crash is a bad access, and it actually shows us that the address that caused the fault or the crash is set to 0. So very quickly, we can already see, yes, this likely is a null pointer dereference. The next thing that you will find in the crash report, which is super important, is the faulting instruction and a stack backtrace. So the faulting instruction, and I will mention this many times, is the location of the instruction that actually caused the exception or fault. This is the last thing that the CPU tried to execute, which triggered a crash. And oftentimes, this is where the bug is, or in the case where it's not, this is a good starting point. So often, we will start at the faulting instruction and work backwards to figure out exactly what went wrong. Now, a lot of times, this faulting instruction will be deep within, for example, a system API. More likely than not, the API does not have a bug in it. It was invoked incorrectly. Perhaps it's a memory freeing routine that was past the null pointer. That's obviously going to crash. That's not a bug in the API. It's a bug in the caller. So from the stack backtrace, we can figure out, by looking backwards, who called the code. And ultimately, this will allow us to figure out what went wrong. We also have the crashed thread state. This contains the values of the registers that occurred when the crash happened. This is also super important because this gives us context. A lot of times when we look at the faulting instruction, it'll just be some assembly code that references some registers. And if we didn't have the values of the registers, we would not really know what went wrong. Now, these registers are going to be specific, for example, to the operating system, or at least the architecture. On macOS, this is going to be ARM64. We could do a whole talk about reversing ARM64 and what the registers are. For example, register X0 through X7 are how registers are passed. Maria has written an amazing book all about this, so I would recommend that book. It's a great read to get really into the topic. The next thing we have in the crash report are loaded binaries. This is also important because perhaps the fault, the exception, the bug is not within the main binary, but in one of its loaded libraries. Also, this has the address that the binary was loaded when the exception occurred. And this is actually very important because, as you will see, what we normally do is find the faulting instruction from the crash report. And then in a disassembler, we load the binary that has the bug. Well, on the file system and in memory, there's going to be an address mismatch because the operating system shifts around binaries when they're loaded in memory due to things like ASLR. So what we need to do is look at where the binary image was loaded in memory, then go into the disassembler and tell it to rebase the image so that then all the addresses will match. Finally, we have the address of the faulting instruction. I've already mentioned this a few times. This is normally when this is where we start. So back to our crashing application, we can see that the faulting instruction is in the main I will crash binary at an address that occurs at F78. So if we load then that binary into a disassembler, rebase it so the address is aligned, and then go to that address, we can see some assembly instructions where the fault occurred. In this case, it's a store instruction where it's trying to store the value in the W8 register into the X9 register. And since we have the crashed thread state, we can see that the X9 register is 0. And so again, if you try to dereference 0, this is going to cause a crash, which again confirms that indeed we have a null pointer exception. So even if we didn't have source code, we now exactly know where there was the issue and also exactly what was the issue. OK, so that's crash report basics. Let's now make it a little more exciting and talk about some real-life examples. Now, up till about a week ago, this was a Mac-specific talk, but then CrowdStrike came along and really gave us a great case study that I alluded to earlier. So let's briefly look at that. So once we have a crash report from a system that had CrowdStrike installed with its buggy channel file, we can load it in WinDBG. This is the program on Windows systems that can parse crash dumps or crash reports. And yes, there's going to be a few differences from macOS, but actually we'll see there's a ton of commonalities. So even though, again, this talk is mostly about macOS, conceptually it also applies to Windows as well. So in the crash report, we can see 3 very important things. We can see the address of the faulting instruction. So this is the instruction that the CPU executed that caused the crash. And then we can also see the thread state that holds the addresses or values of the registers at the time of a crash. And finally, we can see that WinDBG has pointed out that the address that was attempted to be referenced was invalid. It was unmapped. So we already now know the faulting instruction. Basically, they were trying to dereference the R8 register. And since the R8 register is invalid, we know that this is going to cause a crash. So we don't know exactly why yet, but we already know it's not an all-pointer dereference. We know this was a fault in CrowdStrike's driver. And since also we have the address of the faulting instruction, we can now disassemble their driver to figure out exactly what went wrong. And so we do that. Top left of the slide, we can see 1 and 2. If we look at 2, that's where the faulting instruction occurs. As I mentioned, it's dereferencing R8. So the goal is to try to figure out why the R8 value is invalid. What went wrong? So if we look a few instructions back, where we see the number 1, we can see that the R8 register is populated by extracting a value from an array. The RAX register holds the base of the array, and the R11 register holds the index of the array. Now, since this crash report also has some memory contents, we can actually look at that array. It's the bottom of the screen. And we can see that the values from 0 to 19, the first 20 values in the array, appear to be valid pointers. But as soon as we get to the 21st element, which is index 20, because arrays are 0 indexed, we can see that clearly appears to be invalid memory. And also, that is the same address that was dereferenced that caused the crash. So very quickly, we can see now that what appears to be happening is they are indexing outside the array, pulling some arbitrary value, which happens to be invalid memory, that when they then dereference, blows up and causes essentially a global shutdown. And this was ultimately confirmed later by CrowdStrike when they published, as of yesterday, exactly what went wrong, which confirmed this analysis precisely. Now, the cool thing about this is not only did we debunk the claims that people were blaming Microsoft or that there was a null pointer exception that CrowdStrike should have detected, we also revealed the truth of exactly what went wrong. Even cooler, I got a call from Good Morning America because of my crash report analysis that I had tweeted about. And they were like, will you come explain to the general American public what went wrong? And I'm like, yeah, I mean, I can try. And so I got to be on TV. I got my 15 minutes of fame thanks to crash dump analysis. So, you know, that's kind of neat as well. And then my mom was like, can I have your autograph? So I laugh at this. I'm not sure if she was trolling me or not. But again, I never thought, you know, crash report analysis would get me on TV. So kind of another neat thing that we can gain from learning how to understand crash reports. OK, so that was Windows. As I mentioned, the majority of this talk is really focused on macOS. So now what we're going to do is look at crashes from macOS. And you might be wondering, OK, how do I get these crash reports? Patrick, you've made some excellent points. I'm already falling in love with crash reports. I want to analyze them. This is a great question. And it turns out on macOS, you just have to use your computer. So all the crashes I'm going to talk about for the remainder of the talk, save for one, which was also still my fault, actually came directly from my computer. And me just using my computer or running tools that I had written, but like inadvertently, meaning I wasn't looking for vulnerabilities. I was not trying to make the system crash. So I don't know if the takeaway is like macOS is super buggy, but like there's lots of crash reports. Again, just from using macOS normally day to day. And this is a great example. I was writing a DNS monitor. We'll talk about this more. It's a network extension. And I had a bug in my code. I'm human too. And so my DNS monitor crashed. But when it crashed, NSLookup, which was the tool I was using to test my tool, also crashed. And then worse, the network extension session manager, a root system daemon, also crashed. And so I was just like, y'all, like everyone's crashing. And this is not ideal. Like my code crashed, that's fine. But why is it taking down all these other processes? So again, macOS, clearly some room for improvement. I don't mind because this gives me some really interesting crash reports to dig into. And let's do that now. So let's start with Lulu. Lulu is actually a tool I wrote. I am, picking on CrowdStrike, picking on Apple. Well, I'm going to pick on myself as well because it's important to understand that all software is going to have bugs. So I got a crash report from Lulu, and looking at it, I was like, I'm not sure exactly what's going on. It says there's an exception, a bad access, but the memory address doesn't, it's not a null. It's kind of strange. But as soon as I looked at the stack backtrace, I noticed it was a very deep repeating call stack. So the same function was being called again and again and again and again, like hundreds of times. And when you see this, this is very indicative of an issue with recursion that leads to something called stack exhaustion, which basically means you use up the call stack. And so as soon as I saw that, I was like, damn, I know exactly what went wrong. So previously, I had implemented some logic in Lulu, and I decided to do this recursively. I remembered learning about recursive in my computer science class, and I was like, I always want to use recursion. So basically, what Lulu was trying to do is handle something referred to as related flows. The idea is, imagine the user installs a new browser. When it accesses the network, Lulu is a firewall. It's going to pop up and say, hey, something is accessing the network. That's all well and good, but if the browser is opening like 30 tabs, I shouldn't alert the user 30 times. I should alert them the first time, and then based on what their response is, take the same action. If they allow it, I should allow all the other connections. So Lulu queues up the other connections and then recursively processes those when the user responds. This is all well and good until you get something like 300 related flows, which then causes a stack exhaustion issue due to the recursion. Basically, the stack on macOS is not big enough to handle that. So as soon as I saw this, I realized, OK, that's a problem. And so I went back to implementing an iterative approach. And so even to this day, I've never used recursion, which I'm a little bummed about. Next up, we have Yara. Yara is a widespread signature scanning library. It's used in a lot of antivirus products. And I was testing it in one of my tools, and I noticed this like random crash. So I looked at the crash report, because again, I'm always super interested anytime something crashes. And I looked at the exception type in the crash report, and it said bad access, which wasn't surprising. But then the reason it said was code signature invalid. And I was like, OK, that's super weird. So I did more testing, and I found out what was happening is this crash would occur when I was scanning a unsigned binary or a binary with an invalid signature, which is super weird. Apple, though, has an implementation of Yara. I was testing the open source public one. And so what I did was diff the two. And basically, I found that when Apple mapped in a binary to scan, they did so with a Apple-specific flag, which is map resilient code sign. Turns out on macOS, if you map a file, even in a read-only manner, just to scan its bytes, if that file is a binary that has an invalid signature, if you don't map it with this specific flag, when you go to try to read that memory, for example, to scan it, macOS freaks out and says, hey, this is not signed, and crashes, which is kind of makes sense if that was an executable you were running. But for like a read-only scan, that's kind of problematic. So from the crash report, though, I was able to understand exactly what was going wrong. Yara was not using this flag, so macOS was freaking out and causing it to crash. And so I was able to create a bug report that contained a crash report. But also, from the crash report, since I understood exactly what was going wrong, I could provide a lot of really useful information to the developer. Instead of just saying, hey, Yara sometimes crashes, like that's not helpful to them at all, I could say it crashes on macOS when scanning a binary that has invalid code signature because Yara is not using this specific flag. You should copy what Apple does and do this. And so when I submitted this to Yara, the developers were stoked because it provided enough information. They were able to very quickly push out a patch. So kudos to them. And they were like, thanks for the very complete bug report. So again, this is an example of if we understand crash reports and software crashes, if it's a bug we want to get fixed, we can provide that information, which really empowers the developer to do that quickly. And if we look at their patch, all they did was now they map files with that Apple-specific flag. So even if they scan a binary with an invalid signature, macOS no longer freaks out. So Yara is stoked, and this means all the AV tools that use it will no longer crash on macOS. The next crash I want to talk about is in Adobe's Crash Reporter. It's kind of a silly bug, but caused me to laugh for days that Adobe's Crash Reporter was crashing. Kind of ironic. And if we look at the crash report, we can actually see some application-specific information that tells us exactly why it crashes. It basically said CF release is called with null. CF release is a function that releases memory. You can't invoke it with null. If you do, it'll crash. And again, this is not a bug in the API. It's rather a bug in it being called. So now what we have to do is we have to look at the stack backtrace to see who called it, who is responsible for invoking this API with null, because that's where the bug is. So if we do that, looking at the stack backtrace, we can see that the Adobe Crash Reporter calls an API that can return a null pointer. They don't check this, and they always free that, which is problematic, because if you try to free a null pointer, that's going to crash. So the solution would be simply check this. I asked ChatGPT how to fix it, and it's like, yeah, just check the return, and if the return is null, handle that gracefully. Don't try to free it. Next up, we have one of my other tools, Do Not Disturb. You might be thinking, wow, Patrick, your tool sucks. No, no, no. In this case, it turns out to be an Apple bug. But I didn't initially expect that. So I ran this tool, and I came back to my computer, and again, there was a crash. And I was like, what's wrong here? And looking at the crash report, I could see it crashed in one of Apple's security frameworks, specifically in the SecError API. I assumed that this was a bug in my code. I was like, there's no way that there is a bug in Apple's core security framework that I am inadvertently triggering. So from the stack backtrace, I found where in my code I was making a call that eventually got into this API. And it was very simple. I was basically copying a public key, and the key object I was passing it was valid. So I was like, OK, I don't think I'm doing anything wrong. This is pretty straightforward. Let's take a closer look at that SecError API, because maybe there's a bug in macOS. Maybe I shouldn't hold Apple in such high esteem. So what we do is, from the crash report, we find the address of the faulting instruction. We load the security framework into a disassembler to find the actual disassembly instructions of that faulting instruction. We can see what they are doing in the middle of the slide. They are trying to dereference the second argument, which in this case is somehow invalid, which is causing a crash. Since the security framework is actually open source, we can now map that disassembly to source code, which is always super nice. You can more likely see what's going on when you're reading source code. And we can see it looks like a pretty innocuous instruction. They're basically checking that a pointer is not null, and then if so, they are dereferencing it. But we know that this is apparently crashing. So if we look a little closer, we can actually see, even though they declare this error variable as a pointer, they never initialize it. And if you try to dereference or use an uninitialized pointer, it's going to point to random memory, which at best is going to cause a crash. At worst, this is going to introduce an exploitable memory corruption vulnerability. And the kind of hilarious thing is if you actually loaded the source code for the sec error API to open source into Xcode, Xcode will like yell at you and be like, yo, this code is buggy. You are referencing a pointer that has never been initialized. So I don't know what Apple does to compile their code, but like if they literally just looked at the compiler warnings, they would have seen this bug. So I reported this to Apple. They patched it. They actually assigned it a CVE because they said, yeah, this is very problematic. This is a bug, an uninitialized pointer in one of our core APIs. This is something that should be fixed. Staying with my tools, I again was testing another tool. So yeah, I test my tools a lot. And I was like out surfing, and I came home, and my box had not just like crashed, it had kernel panicked. I'm a little strange. When my computer panics, I get really excited because I'm like, maybe it's a kernel bug, right? And so yeah, I know I'm weird. So I looked at this, and I was like, this is strange. I ran my tool. A few hours later, it kept crashing, and I was like, weird. My tool runs in user mode. User mode tools should not cause the box to panic. That's the whole point. They run in user mode. So I looked at this kernel crash report, and I noticed a few things. First, we have a page fault, and then we have the faulting instruction, but also the address of what is unmapped memory. So again, we start with the address of the faulting instruction. We find that in disassembly. And again, because this part of the kernel was open source, I could find the source code that mapped to the buggy instruction. Basically, they were checking a path to see if it was null terminated. And if we look at that, we're like, that looks kind of OK, but it's crashing. Why? Well, it turns out they had a off by 1 error. So what they did was they calculated the length of the data and then used that as the index to see if it was null terminated. That's problematic because, again, since arrays start at index 0, if we want to look at the last element of the array, you have to do length minus 1. And this normally wouldn't cause a problem unless the path they were checking happened to end exactly at a page boundary and the next page was not mapped. And in that case, it would be an out-of-bounds memory read, which would cause a kernel panic, just like CrowdStrike's bug. So I reported this to Apple. Like my tool was like inadvertently triggering this, and like if I do that, users yell at me, even though it's not my problem. And Apple's fix was like, I can't understand it. So again, remember they're trying to like check if a path is null terminated. And there's a comment in the code that says, make sure the path is null terminated. And their fix was to add a stir copy, specifically a stir L copy. Now, many of you might know this, but what a stir L copy function does is copy bytes until either A, the buffer is filled, so it doesn't overflow, or B, it encounters a null byte. Well, as the comment says, we're not sure this is null terminated. So like if we just are blindly copying until we hit a null byte, this means now we've just introduced a information leak. And also, this will still crash if the path happens to be aligned with an unmapped page. So I was like, Apple, I mean, like, not only did you not fix the bug, you actually introduced a info leak. Like, what are you doing? So I reported this to them as well. And while they were fixing this, I said, you know what? I'm going to look at the rest of this function because clearly it's buggy. There's an off by 1. They have no idea what's going on here. Are there other bugs? And it turns out, yes. Like 2 lines above it was a memory copy or a B copy that was actually incorrect and would lead to an exploitable kernel heap overflow. That's really problematic. And again, we got here from a crash report. Now, this next one is maybe not the most interesting bug in terms of what it was. It was a null pointer exception. But there's kind of an interesting story about it, which was my friend started complaining. And she said, Patrick, every time you text me, my phone crashes. And I was like, what? And she's like, are you trying to hack me? And I was like, rude. I wouldn't use my hacking skills for personal gain, and also my exploits don't crash. Like, I was very offended. But she's like, no. Like, let me show you this. So I went and looked, and indeed, every time she typed the word Taiwan, her phone would crash. And so she's like, maybe the Chinese are trying to hack me. And I'm like, I don't think so, but like, let's figure out what's going on, because like, you shouldn't be able to remotely crash iPhones, right? So what do? We get the crash report. We start looking at the crash report, and we can see that the exception information appears to show that it's a null pointer dereference. So not like a super interesting bug in the terms of exploitability. But if we look at the call stack, we can see that it appears to be related to emoji processing, which makes sense because I would text her a lot of emojis, and also it triggered when she would try to type a word that would trigger macOS to suggest an emoji. So looking at information from the crash report, we have the crash thread state. We can see it's crashing in a stir compare function, where the string that's being passed is null. So again, this is an example of not a bug in an API, but rather incorrectly calling an API. You can't do a string comparison passing in a null. I mean, maybe Apple could check for this, but this is pretty standard that that would crash. So the question is, why? So I looked at the disassembly in the call stack, and I basically found that what Apple was doing was trying to get the locale of the user's device, and then comparing that with CN for China. If that was true, they would not display the Taiwanese flag. So that was interesting, because basically it showed that Apple had acquiesced to the demands of the Chinese government and was like, yeah, sure, we can censor content on the iPhone, which I think is kind of, well, I won't go on a rant about that. But Apple claims to be for the users, and then they're like agreeing to censor stuff. So what they were trying to do is censor the Taiwanese flag on Chinese phones. And I guess the takeaway here is Apple seems to have no problem, like, again, acquiescing to the demands of the Chinese government, but also like does this incorrectly. So like if you're going to introduce censorship code, like at least test it, I guess would be my suggestion. Who knows? All right, so those were some, in my opinion, very interesting crash reports that revealed exploitable kernel heap overflows, crash reporters and bugs in crash reporters, Apple censorship code. Those were somewhat historical, but I do think showed the value of crash report analysis. I now want to shift gears a little bit and talk about more recent crash reports that reveal what are all currently still 0 days in macOS. Again, all from my computer, me not trying to find bugs. So the first one is in Apple's Keychain Access app. And so I was using the keychain, and it generated a crash report. And I was like, that's strange. So I looked at the crash report, and if we look at the reason for the crash, we can see that the operating system has detected a pointer authentication failure. This indicates that something was freed or released, and ultimately it was corrupted. If you see a pointer authentication failure, this is indicative of usually very interesting memory corruption vulnerability. So you might want to look into that to see if it's exploitable. And to me, it was interesting because the keychain access application has the access rights to everything in the keychain, which includes your passwords, your certificates, and all other things. So if we look at the stack backtrace in the crash report, we can see that it starts with a bunch of calls to various Apple security APIs, including the certificate get data. So I decided to debug the application to get more insight into what was going on. So I set a breakpoint on this method. And once that breakpoint was hit, I simply printed out the values, specifically the arguments. And in LLDB on macOS, the PO debugger command will print out an object. And in this case, we're printing out the address or the value of the first parameter, the first argument, which is in the X0 register. And we can see LLDB tells us not only its value, but its type, which is very important. And we can see its type is a key object. This is strange, because if we go read the documentation for the certificate get data API, it expects not a key object, but a certificate object. So basically what Apple is doing is, in some scenarios, the keychain access application is passing the wrong type of an object to an API that expects one type of object. It's passing a key object instead of a certificate object. And this is very problematic because this is an object type confusion vulnerability, potentially exploitable, but if nothing else, like just a bad bug. Next up, I want to talk about an interesting crash in Apple's system extension daemon. A little bit of backstory. What is the system extension daemon? So about 5 years ago, Apple decided to deprecate third-party kernel extensions. And when the CrowdStrike fiasco happened, Apple was like, this wouldn't happen to us. We were smart enough to kick everyone out of the kernel 5 years ago. And that is correct. And Apple should be lauded for that decision. The other thing that Apple did that was very important is when they kicked everyone out of the kernel, they said, we are going to give you new frameworks that allow you to build the same type of tools that previously lived in the kernel. These tools will have the same power, the same ability, but if they crash, they won't take down the entire system. They also won't be easily unloaded by malware. And this is really important because when people talk about Microsoft kicking kernel extensions, third-party kernel extensions, there's people who are like, this is a bad idea because malware will then be able to like own these tools. And it's like, no, Microsoft would likely or would have to provide similar extensions or frameworks that would allow developers to write the same kind of tools, but that would run in user mode. OK, that's relevant because the system extension daemon is the component that runs in user mode on macOS system that allows us to create these new security tools that have the same power, essentially, as kernel extensions that run in user mode. So it's very important that this is written well. So I was writing a system extension. I was porting one of my tools out of the kernel and testing it. And my tool had a bug, seeing a theme here, I guess. But interestingly, like, it ended up crashing Apple's system daemon. And I was like, that's not good. Like, even if I have a bug in my code, it shouldn't crash Apple's component that's running this core component. Looking at the crash report and looking at the call stack, we can see that the faulting instruction is in an assertion. And if we disassemble it, we can see that what the system extension daemon is doing is handling some error case by throwing or validating an assertion. But if that assertion fails, instead of handling that gracefully, it decides to crash, which is like an interesting design decision. So I decided to look for other assertions that perhaps were easily triggerable. And very quickly, I found one. If you ask the system extension daemon to load a new system extension, it validates the architectures. And it does this because on macOS, you can have what are known as FAT or universal binaries that have multiple architectures. For example, Intel, ARM64, et cetera, et cetera. So it makes sense that the system extension daemon should validate that. And so we can see a checks to make sure the architecture count is not 0. That would be an invalid file. But again, if it detects this, instead of like just refusing to load the extension, it throws an assertion failure and crashes. So this means we can take a extension, we can nop out the number of architectures, set it to 0, request that the system extension loads this. We don't need any special permissions or privileges to do that. And this will cause a repeatable crash. The impact of that is if we do this over and over, we can prevent any other security tool from loading. So this isn't exploitable because it's just an assertion failure. But being able to cause this daemon to crash can have impacts for other security tools. Now, the last bug I want to talk about is in Apple's Network Extension Session Manager. This is probably my favorite bug, maybe because Apple's been begging me to like give them details about this, but I was like, no, I'm going to save it for y'all. I want you to be the first ones to learn about this. So Apple's Network Extension Session Manager is somewhat related to the System Extension Manager. It handles a certain type of extension known as network extensions. And these are things like firewalls. So if you're writing a firewall on macOS, using the new approach, it's going to run in user mode as a network extension. So the Network Extension Session Manager manages these. So again, I was writing this. I had like a bug in my configuration. And when I tried to load my network extension, it crashed. The crash was kind of interesting, not a ton of information, but it basically showed that there was invalid memory access in what is the respond to selector method. This is a method related to Objective-C calls, and if you see a crash in this function, it means it was likely invoked with a corrupted object. So I was like, that's interesting. Let's look into this more. So what was this object type corruption? Basically, what the Network Extension Manager was trying to do was build an error message using a format string. It requested a format string using a key and also specified what it expected the format specifiers to be. The format specifiers are the things that follow the %, and these have to match the type of object that you put in the format string. So for example, a %at is the Objective-C way you say, I'm going to put an Objective-C object into this format string. It's a placeholder for an object. On the other hand, if you put a %s, you say, I am going to give you not an object, but a traditional C string, which is just a sequence of bytes. So the Network Extension Manager requests this localized string to build a log message. But if you look at the string it gets back, the last format specifier is not a %s, which is what it asked for, but really a %at. And if we look at the disassembly, we can see that it then invokes the NS string init with format to populate this format string with a C string, which is what it asks for, so that's what it expects the format string to be. We can confirm this in a debugger, basically showing this object mismatch by showing indeed the format string that's about to be populated does contain as its last format specifier %at, which again says you should give me an object, when in reality what they are passing in is not an object but a C string. This is very problematic because if you pass a C string into something that expects an object pointer, it's going to crash horribly and maybe even be exploitable. However, what I noticed was, instead of trying to exploit this for a privilege escalation or whatever else, that when the network extension session manager crashed, it would actually unload every other network extension. This means any other security tool that was running on the macOS system could be unloaded. This is very problematic because this is one of the things Apple promised would not happen if we moved our tools out of kernel mode. Because one of the things is, if you're running in kernel mode, user mode malware can't just be like, yo, unload yourself. So this is problematic because, again, the impact is malware could make a request to the network extension manager with no special permissions, give it a corrupted or malformed extension, trigger this crash, and thereby indirectly cause any other network extension security tools, firewalls, or anything else, to be unloaded. Because when the network extension session manager goes down, it takes all the other third-party network extensions with it. Not cool. This also has some impact on the network, so there's some potential impact here as well. Ransomware, for example, could kill the network to prevent backups and then start maybe encrypting all the files. Or a lot of security tools gather events and do cloud-based analysis to detect malware. So this gives malware the opportunity to prevent that as well. Now, I could talk about crash reports all day. I don't want to put you to sleep, but there's like so many more. And again, these are just like from my computer. So there's like crashes in like the Bluetooth daemon and in like payment processor extensions and in the Windows server and in virtualization. So like macOS appears to be very buggy, and as I've hopefully shown, these crash reports can reveal sometimes some very interesting bugs that clearly have security implications. Some of these, like the ones I just talked about, even on the unreleased macOS 15. Now, I briefly want to end by talking about crash report monitoring, because at this point, you're probably like, yeah, crash reports are cool. How do I, for example, maybe monitor for them in my enterprise so that I can collect and analyze these? Well, it turns out it's pretty easy. The idea is just monitor the crash report directories, and then when new crash reports show up, grab those and perform some analysis. So we can do this with endpoint security. I'm not going to really walk through all this code. It's more for reference. But the idea is what we can do is we can tell the operating system to watch a specific directory, and then when files show up in there, we will get a callback. We use, as I mentioned, endpoint security and a technique known as mute inversion. You can tell endpoint security to mute specific events, but if you invert that, the logic is flipped, which tells you, hey, only give me very specific events. For example, file creations in the crash report directory. Now, I do want to point out that, say you start collecting crash reports, the majority of them are probably going to be uninteresting. I definitely picked what I thought were the most interesting ones today, but the reality is a lot of applications crash, and that's maybe annoying, but they're not going to have security implications. It's not going to be malware, et cetera, et cetera. So here's an example from Xcode. It crashed when I was like clicking a menu. Like the fact that Xcode crashes, annoying, but like no one's exploiting Xcode, right? It's an IDE. Also, it requires user interaction, so like it's not going to be like really exploitable per se. So what I always do is when I get a crash report, I ask the question, is this a process of interest? If it's keychain access app, yeah, that has a lot of access rights. Is it a daemon that's running with root privileges that might take down other security tools? Yeah, that's super interesting. But if it's like Xcode or calculator, I'm like, I don't care. If the crash is due to an assertion, that's probably not interesting because that's not really exploitable, unless that's in something like a system daemon. We talked about how being able to take that down allows malware, for example, to prevent other tools from loading. And then finally, if the crash is on the main UI thread, generally that's not interesting. Apple's UI frameworks are notoriously buggy, and they crash, but again, that like requires user interaction. And it's going to be some crash and some rendering thing that like an attacker couldn't really take into account anyways. All right, so some conclusions and takeaways. Wrapping this up. So hopefully I've shown you that crash reports are your best friends. They can allow you to find bugs that you can fix or exploit, if that's your thing. No judgment. It also gives you the ability to uncover malware, failed exploits, and much, much more. So we're going to end with another raise of your hands to see who here now loves crash reports. Everybody? More people? See? Love is still alive. So that's awesome. That makes me very happy. And speaking of love, I want to end by thanking the companies that support the Objective-C Foundation. These are the companies that allow us to host the amazing Objective by the C Security Conference, support the free open source security tools that are well tested, even though sometimes they crash macOS, and also the student scholarships and everything else we do. So, round of applause for them, but also for all of you for attending my talk today. Thank you so much. I really appreciate it.